Hey folks, this is David with Streaming Relativity, home of the Astro DNA Observatory. And you guessed it, the Astro DNA Observatory is more than just an observatory in the backfield and more than a studio upstairs where I make my videos. It's also a workshop. The workshop is where I do everything with my telescope rigs and particularly setup and testing. And you'll notice that on the bench today we have a Celestron C11 XLT with star-bright coatings. Now this is not the Edge HD telescope, and that's okay. It's okay because this is a phenomenal instrument that you can get on the used market for a very reasonable price. I picked this up on the Cloudy Nights Classified forum, and I am so excited to put this to work for me. And today what we'll do is we'll talk about the SCT design itself, how what they're intended for. And we'll go over the physical build of the C11 and some of its features. And then finally, I'll wrap up with what my intent is with this rig in the observatory. What are the use cases that I have in mind? I might even share some observing. Okay, folks, stick around. It's going to be a great video. Okay, cool. Let's start with the design of this telescope. The C11 is a Schmidt-Cassegrain Telescope, and that is a revolutionary design because it allows for very long focal lengths in a very compact design. This thing is relatively small, the OTA, relative to its focal length. So how does the SCT do this? It does this by employing several optical components, and it starts with a corrector plate, and that's in the front of the tube. And what that's doing is it's reshaping the wavefront of the incoming light so that there's a reduction in the aberrations that result from the primary mirror design. The primary mirror at the back of the telescope is the second optical element in the design, and it is spherical. And as a spherical mirror, there's going to be spherical aberrations, which the corrector plate is trying to adjust for on the incoming light source. So the diameter of this primary mirror is 11 inches, and that's a huge amount of light gathering capability. That light gets reflected back towards the front of the telescope and focused down onto what we would call the secondary mirror. That's also a smaller spherical mirror. The secondary mirror takes the light and then focuses it down and out the back of the OTA where it hits your image train, right? So the focal plane is exiting the back of the telescope. Now some SCTs, like the Edge, they incorporate a fourth element, which is a lens element at the rear of the telescope to flatten and further correct the field at the focal plane. And non-edge scopes, like the scope that I'm sharing today, can use a corrector or focal reducer to serve a similar purpose. Now, I typically use the corrector with my SCTs when I'm imaging DSOs, but I do not use them for most of the use cases, which would be for lunar and planetary imaging. So this 11-inch scope has a focal ratio of f10. That results in a focal length of 2,800 millimeters. Now that's huge compared to, for example, I'm currently using a 90 millimeter I'm using a 90 millimeter aperture or a 540 millimeter focal length scope in the observatory right now. So this is so much longer in terms of focal length. And obviously that's a lot of reach that this C11 telescope is going to give me for certain celestial objects. Now, obviously the planets are small. And because of that, we want more focal length. But this also applies to faint distant galaxies or small planetary nebula. So there are lots of targets in the night sky that benefit from a longer focal length. And of course, these telescopes are also perfect for digging into small lunar features. And you can even equip them for solar observing, but do so with a lot of caution. Okay, SCTs, look, they're great scopes for observing. They're great scopes for imaging, and I tend to use them for their focal length. But others use adaptations on these scopes to do to reduce focal length and make them much faster for wider fields of view. And so they're taking advantage of the aperture in that case. So, more light, more data, less integration time. And so and for those that are curious, those adaptations include, there's an old system called FastStar, and then there's the newer HyperStar, and effectively that takes these scopes, which are natively f10, and brings them all the way down to f2, super fast system. So bringing those all the way down to 560 millimeters of focal length. But again, my intended use cases are longer focal lengths. Okay, so we can see the versatility of the SCT design, but it does come with a few challenges. The first is that the enclosed design of the SCT will often require a lot of time to reach thermal equilibrium with the outside environment, and this is to avoid any kind of image distortions due to thermal gradients within the tube. So cool down time or adjustment time, a temperature acclimation time is key. Second, dew formation. That corrector plate is prone to dew formation. So you'll need some combination of dew shield, dew heater, maybe a dew heater ring to help mitigate that circumstance. The famous mirror shift and mirror flop. This is when the primary mirror shifts slightly when the SCT is focused, or it flops more dramatically when the telescope's orientation shifts in a significant way, such as what happens with the meridian flip. So this can be very annoying, and it can even affect guiding. It could affect the framing of your shot, and it even can throw collimation off. So you're going to have to learn how to deal with this with your specific telescope, and that might include employing an external focuser and possibly implementing some kind of locking mechanism for the primary mirror. I have not had to do that thus far with all my SCTs, but I know many that have. So speaking of collimation, SCTs will need more frequent and precise alignment of those optical elements in order for it to perform well, and that can be challenging for beginners who have never done it before, but once you learn how to do it, it's not that terrible. You just need to make it a part of your periodic workflow. Finally, and probably the most difficult challenge relative to SCTs is that when you have these long focal lengths, this is going to magnify tracking errors and any imperfections you might have in the guiding of your mount. So this means that the guide scopes that we use with an SCT are typically longer and heavier. And that means that we're going to get some differential flexure if we're not mounted properly, and that's when the guide scope is moving differentially from the main scope for whatever reason, stresses, torsions, etc. And that results in really poor star shapes, which are amplified with these long focal lengths. Many people choose to use an off-axis guider with their SCT, and I would recommend that for deep sky objects because this is going to, eliminate the flexure issue, and it does that by basically taking the same optical path as the main imaging camera and guiding off of that. So there is no difference between these the guiding path and the imaging path. And but these can be difficult to configure. You've got to get them right, and they might not work well with targets where there are limited available stars in the field of view around your targeted object. But I will say that all these challenges can easily be dealt with. After all, when you think about it, SCTs have been used for both observing and imaging for decades. Okay, so hey, let's take a look at the actual telescope. Okay, with the design of the SCT covered, let's talk about the physical implementation of the Celestron C11. And let's start by recognizing that this entire thing is what we call the optical tube assembly, and it's made up of a number of components. It weighs about 28 pounds, so that's without the image train. So if you're thinking about a mount, I think you have to assume a mount that can handle minimally 50 pounds, perhaps 60 pounds. Although I have used this without guiding. I've already used this on my Ioptron GM, the 45, and that was for visual purposes and lunar. So you can get away with it. You can get away mounting this, under mounting this if you're just doing observing or lunar or perhaps even planetary. Okay, so in terms of its overall dimensions and size, it's probably around, the OTA itself is, with the cap off, is, if you include the rear cell, we're just under 2 foot. So it's about 24 inches in length and obviously diameter. It's an 11-inch primary mirror. Add for the casting and the casing, you're probably looking at a 12-inch diameter easily, perhaps a little bit more. And yeah, I think it's safe to say 12 inches. Okay, so that gives you an idea of the physical size of the OTA and its weight. You'll notice in the front, we'll start with the front. This is an aluminum tube. They do make this in fiberglass as well. There are some additions of that. It's an aluminum tube. It's closed, right? So it's a closed system. And the tube itself sits, there are a casing in the rear. It's an iron casing. In the front, it's just like a housing. It's a ring housing. So there are screws you'll notice on the rear casting as well as on this front housing that screw into the tube itself. So that's going to give it some structure, and these also serve for positioning other components in the telescope. One last thing on these housings is that they have other screw opportunities placed all around these housings, and that's for things like finder scopes, rails that you can connect. This is a dovetail on the bottom. I'm using a Losmandy D plate. So there's accessory mounting points on these housings themselves. Let's talk about the front. Okay, so really this housing here is used so that the corrector plate and the secondary mirror can be securely attached to the OTA. And so the first thing is that a lot of folks may not know that that corrector plate does provide optical functionality. It's not a clear piece of plastic. It is designed to help coma correct. It's designed to help with the light path to get optimal optical performance at the eyepiece. So that is an important optical element. It also is where the secondary mirror is housing is located in the center of it. And with SCT designs, as we talked about, there is a central obstruction. It's minimal relative to the benefits of an SCT design in terms of achieving larger focal lengths. But at any rate, that secondary mirror is where you'll do your adjustments to collimation. So there are 3 screws within that secondary, within the housing that will allow you to adjust the tilt of the secondary mirror and therefore adjust the light path, the directionality of the light path, and to achieve proper collimation. So, okay, and then obviously there's a cap that ships with the SCT, which you should always place onto your optical tube to protect that corrector plate when you're not using it. All right, so why don't we go ahead and we'll go around, I'll swing this around and we'll see if we can't take a look at the rear of the telescope. Okay, so the rear of the telescope is where all the weight of the telescope is, by the way. You have a primary mirror, which is a spherical mirror, that is inside this iron casting, and the mirror itself
is used to focus the telescope. What I mean by that is that the mirror of this SET, of SET designs, will push forward and can be brought back via a focus knob here. And there's an arm, as you probably highlighted in the design discussion. So that mirror has a hole in the center, and it's lubricated inside the casing so that as the focus knob is either racked in or out, the mirror will slide within the casing over a central optical tube, which is the light path from the secondary mirror will ultimately travel through out into the eyepiece. So how does it get there? Well, there's an opening on the back, obviously, at the center of the SET, and this is where you connect your optical accessories for viewing and for imaging. And I do have a number of those accessories here, which we'll talk about, but for purposes for now, just know that it typically begins, it's going to begin with a visual back, as if you are doing visual, and that's what we're going to talk about today anyway. We'll talk about visual. So there's a visual back. Now the threads on the Celestron C11 and C14 are 3 1/4. So the visual back will have 3 1/4 inch threads here. You can, and this is a 1 1/4 visual back, meaning it's designed to take 1 1/4 inch nose pieces from here on out. So there are 2-inch backs that are available for it, and over time I may invest in one. And there's also, Beta has, I think, click lock solution, because this is worse than compression rings. Right? The standard visual back is you're using 2 set screws to basically tighten down on whatever 1 1/4 inch nose piece that you're going to put in here. And aside from visual viewing, and even in the case of visual viewing, I just don't find that to be a really secure connection. But it's good enough for me for now. And at any rate, so you have your visual back, which screws into the 3 1/4 inch thread, which right now is being covered by this cap. And once that's threaded in, then typically what you'll wind up doing is introducing a diagonal into the mix with a 1 1/4 inch nose piece. So that again will insert into your visual back, and regrettably, you're going to be dependent upon these screws to secure it. Now, remember, when you're slewing to a target and you're finding your target, your telescope, is going to wind up finding itself in different orientations. So the idea that you should be able to rotate your your diagonal so that your eye is comfortably looking through the telescope, depending on the orientation of the OTA after you point to your target. So at any rate, this gets you to your diagonal, and then from your diagonal you can generally just go to an eyepiece, and there's so many different things you can do here. I'll give you an example. This is a 3x Barlow, which again, 1 1/4 inch nose piece can be inserted into the diagonal, and then of course you can insert your final eyepiece, whatever that might be. I think I probably have a 25mm or a 40mm Plossl here. And then your eyepiece, okay, can slide into your Barlow. So this is going to, so if you're not familiar with what a Barlow will do, it'll take the focal length of your telescope. In this case, this is 2800mm focal length, which is quite long, and this will triple it. So that's an amazing focal length that you can achieve. And then of course, depending on the aperture of your eyepiece, you can either have a wider field of view or a more narrow field of view, and so you can get extreme magnification. And I will tell you that it is so much fun to put an eyepiece into your telescope and to look at easy targets like the moon, and to study all of its features at such levels of magnification. It's a very rewarding experience. One thing I will point out is that as you are increasing your focal length through Barlow's and other things, the image will become dimmer and dimmer inside the eyepiece, and that of course is optical. We know that from optical theory. So, at any rate, this is a visual setup, and then I'm just going to add one other thing to it for now, and then future videos we'll get into planetary, which is right around the corner. We're about a month away from launching planetary, which is going to be a lot of fun. You'll notice here that I have a cell phone, and there's a plastic adapter which attaches to the body of your phone and allows you to adjust the location of where your eyepiece can be mounted so that it's covering your lens element that is feeding either your video or your photo hardware here. And what's nice about this is that this is a 40 millimeter Plossl. So this I can place into directly into, just like any other eyepiece. I can place this into my diagonal or my Barlow, whatever my optical train may be, and then I can begin to record, and it will capture what I'm seeing in the eyepiece. So we'll take a look at that. Why don't we pause and take a look at that now? Hey folks, it's David with Streaming Relativity, and I'm doing something different tonight. I'm actually going to be doing a little bit of observing with my C11 SCT, and I'll tell you, with astrophotography, you get so obsessed with the imaging that you lose your connection to the night sky if you're not careful. And I know we all love the night sky, and there's a crescent moon tonight, and I thought this would be a great opportunity to exercise the scope. I'm also going to try a little cell phone adapter, see if I can get a little bit of video of what we see in this beautiful 11-inch SCT telescope. So stick around and I'll show you what I'm doing. So what's really cool about cell phones today is that the camera in these things is really high definition, and for about 15 or 20 bucks you can get a very simple adapter that allows you to clamp onto that nose piece, that 1.25-inch nose piece, and then center the lens of the camera straight down into your field of view, and it actually does a remarkable job of capturing really cool video of what you're observing. So here I am right now, and you can see the camera adapter has enabled my cell phone to take video. It's absolutely phenomenal. Viewing and observing these objects is amazing, and it's so different than just purely imaging them. To see them up close, live like this, through the eyepiece, simply amazing.
So let's take a look at the actual images that were captured with the cell phone using this adapter. And I have to tell you that it's simply amazing to look through an eyepiece of a telescope. And the beauty of this technique is that I get to share that with folks who weren't even there. But this is actually what you would see through the eyepiece with the C11.
cool. With that, I'm going to call this video a wrap. I really hope that you guys enjoyed my overview of the SCT telescope design, the review of the build of the Celestron model. Again, they are available at great discounts on the used market. Be careful. Make sure that you find somebody that has the original packing, that really took care of their telescope. I have a wonderful specimen here. I'm really pleased with it, and I'm going to be doing a whole playlist on planetary in about a month. I'll start that. In the meantime, it's back to the refractors, and I will be planning some dark sky visits soon. So with that, I will see you all on the next video.